let's talk about how an enzyme actually works. How does it help a reaction go faster where regular proteins don't do that? So when I've got a protein, I'm going to draw my generic bunch of alpha helixes, some beta sheets, some alpha helixes. Well, what will happen is if we kind of zoom in on a location, so let's blow this one up. You'll have an alpha helix running down one side, and over here you'll have a different alpha helix. And off each of these will be, maybe a polar group, maybe a non-polar group, some non-polar groups here, maybe a very polar group over here. That is, there's side groups coming off the protein. Now, a molecule, if it happens to have something that's very partially positive that can interact there, and so let's say we have a nitrogen to a carbon to another nitrogen, or maybe to an OH this time. And then this side is a long carbon chain and another ring. Say something like that. So I have this molecule that's just kicking around in the body. It's got a phenyl with an ethyl, it's got a ring with a nitrogen. But the idea is one end of it is pretty darn polar, and one end of it is pretty darn non-polar. So we got polar up here, non-polar down there. The idea is what happens is the evolution, the protein changes a little bit each generation, but eventually a protein was created that had non-polar groups at just the right space to interact really well with the non-polar components, and had polar groups at just the right distance to act really well with the polar bits. If these groups had been a little further away, if we had, let me jump for a second, let's say that this non-polar bit was further down, it wouldn't be able to interact. This would be too far away, too big a distance. And so as a result, they wouldn't be able to capture and interact with that non-polar section. But if your groups are just the right distance, if your ordering of amino acids puts them in just the right spots, they can create a little pocket that is good for holding on to that molecule. This pocket where things would fit in, this is the active site. An active site is the spot on the protein where the molecule will stick and reactions will happen, or on our enzyme. So most of this molecule, if we're going to look, and we see a different color here, all of the rest of this, all of those, this top bit, all the rest of that protein, or that enzyme, isn't doing the reaction. The enzyme only has the spot right at the active site actually perform the reaction. The rest of the protein, the rest of the enzyme's amino acids, are there to make sure things are twisted into the right positions, or to anchor it into a cell wall. You could easily have this lower bit be very non-polar, and so you could have it be anchored in the cell wall. We got our dilipids here. And so maybe you want this enzyme to hang out on the surface, but you want it to be out where the water is, either outside the cell or inside it. So a lot of times the rest of the protein's there to position the enzyme where it needs to be, but the active site is where the reaction happens. Well, what makes the active site then? Just a mix of polar and non-polar attractions. These are groups coming off the protein's backbone, the amino acid backbone, they are at various distances. Like, remember, some are coming off other sides. Some are coming off here in the middle, some are coming off there, some are going that way, some are going that way. As they spiral around, or on a beta sheet, as they line up back and forth, there's just certain amounts of space between them. In the right protein, that space is perfectly designed for a certain molecule to fit in. And so this is how an active site works. It is built to hold the target, the substrate, the molecule it's going to react. Well, there's kind of two ideas for how this works. One is, we'll use a generic enzyme. Let's say I have an enzyme that kind of looks like this. And I have some substrate that happens to have this shape. Well, that substrate is just the right shape to fit into our enzyme. I guess I made it a little small on top here, but here, we'll say it goes down here. That is, this can just fit in, the enzyme will grab it, and then whatever reaction is going to happen is made a little easier because the enzyme is catalyzing it. This perfect fit, this is the lock and key model. This is one of the early theories, and it's still kind of used as a quick explanation. Your lock has to have exactly the right height for the teeth on the keys, and when you put it in, it's a perfect fit. Well, there's also an idea that our molecule probably looks a little bit more like this to start, or the enzyme does. Our molecule comes in and, let me fix that. It's got its shape a little more defined. Your molecule tends to be small, and so it has a pretty rigid shape. But a protein, it's massive, and it bends and stretches and flexes. Despite being small atoms are very big, the big structures actually can flex quite a bit. You don't think about it, but the skyscrapers downtown, they can bend several meters in the wind back and forth. Like, they move, and they can bend pretty far because of their size. What happens is, as this attaches, it causes the bottom one, get a different color here, to alter. It causes it to fit better. So it basically kind of smushes in, and it's nearly in the proper shape originally, and then once they meet, it definitely becomes the proper shape. This is an induced fit. You've got to be close, and then it interacts and bends into it when they meet. This is actually the prevailing theory. The idea is, well, they're flexible. They're not going to be in a super rigid position initially. They're kind of going to have some play until something clips in to help hold them together. This is kind of the idea of how the active site works. It just has a certain shape, and it fits a certain molecule of the matching shape. What happens, why this helps it? Well, you can have a molecule like carbon with double bond and some groups. So you have something like this. And you have an enzyme around it. Well, what can happen is, if you want to make this reactive, the enzyme, when it induces the fit and grabs it, can result in the molecule bending a little bit. So we don't really think about that too often. But just a little bit, it causes the shape to shift. And so instead of being, the proper 120-degree angles here, now our angles are a little different. Our double bond is a little stretched. This is less stable. This induced instability, we can stress the bonds by forcing them to bend a little bit when they fit in. We can induce charges. If you've got an R group that has, a carboxylic acid with OH or something, if this is in the right position, you can put hydrogens on. You can slap an H plus on, or you can remove it. You can steal an H plus. So that's a way to destabilize the molecule. You can rip an H plus off, turning it anionic, or you can slap one on, turning it cationic. Depends on the molecule. And honestly, one of the most common, just hold things together. So we don't think about this one as often, but if compound A and B react to make C, they have to find each other. Especially for things that there's very little of, and plenty of times in the body there's very, very little of things. Getting them to find each other is hard. And most of the time when they do, they don't react. So if you can have an enzyme that will capture A on one spot, and it's really good at it. Every time they meet, it manages to grab A and just hold on to it. And it has another spot that can capture B, you can just hold them near each other. Now they can bounce back and forth really fast, many, many, many times. They don't have to find each other in the whole solution. They're right next to each other constantly. So the number of chances they have to bounce into each other goes way up, and so the reaction happens much faster. Sometimes enzymes' only job is to hold the two things that need to react near each other. So that's some of the ways that enzymes can facilitate catalyzing things. They can stress the bonds so that the molecule is more reactive. They can hold things together just so that they're able to find each other more easily. They can destabilize the molecules by putting on or ripping off protons. That's a pretty common also reaction.